Welcome back. Let's talk about um, thin films. Before we can talk about this, we need to review some things that we learned last year. This was a handout that I gave you last year if you were in my class. So I've got a wave coming down this rope in a fast medium, and it's headed towards a slow medium, and when it enters into this slow medium, some of this wave will carry on as is, transmitted into the slow medium, but some of this wave is going to bounce back and head this way, a reflected pulse. If you're going from fast to slow, this interface right here is going to act like a fixed end, and it's going to be inverted, or out of phase by 1/2 lambda. If I have a pulse traveling in a slow material headed towards a fast material, some of this pulse is going to be transmitted unchanged. And I say unchanged, okay, its amplitude is going to be less, but it's going to carry on the same side, and some of it will bounce back on the same side. And here we have it's not out of phase, right? This one. So keep this in mind as we move to talk about light now. These diagrams up above, they were for transverse waves, but light waves will happen, will behave the exact same way. So I got my black pen here. I don't really have access to the other colors. I apologize now. I've got light coming down, hitting in air, hitting some water. It's going from n equals 1 to n equals 1.33. When it hits the water, it will slow down. Now some of this wave is going to carry on unchanged, not inverted. However, some of this wave is going to reflect off the water, and it will be inverted or put out of phase by 1/2 lambda, just as we saw above. And you can pause, go back, and take a look again. The part that bounces back is inverted when I go from fast to slow. Now over here, if I have a light ray that's in glass going into water, I'm now going from something slow into something fast. Some of this will carry on unchanged. It's not really the one I'm usually interested in. I'm usually interested in the one that bounces back. Now in this case, since I'm going from slow to fast, the part that bounces back will be unchanged. Oops. Okay. And we are going to have to do this again and again and again, and you'll see me do it in a question a little further down. So let's talk about what happens to light when it enters a new material. Is the velocity going to change? Yes. Okay. It will either slow down or speed up depending on the end that it's traveling in and the end that it's going into. Will frequency change? This is a tougher question. The answer here is no, and I can show you. If I have a medium and I've got one here, one material here, air, water, and I have light waves coming down, how often they moved into the water changed, what I would have here, let's say it's slowed down, what I would have here is I would have water, I would have these light rays hanging out, waiting before they went. If they were coming in quicker than they were coming out, I'd have a bunch up. I'd have a backlog here, and that just doesn't make sense. Light doesn't hang out at the interface between two materials waiting to move into it. So will F change? No. So if V changes and F doesn't, then lambda will also change. Got to, according to the formula. By how much will it change? There's a little formula here. The new lambda in this new material down here, if this is the old material, light's traveling in it, what I do is I take the old n, divide it by the new n, and then I multiply by the old lambda. So this is a formula that we will be using in every single question. And one of the biggest mistakes you can make is forget to do one of these questions. Do this in your calculation. So now all that preamble, what is a thin film? A thin film is when a super thin layer of some transparent material sits on top of another transparent material. For example, oil on water. You might have seen a nice rainbow type Jesus Murphy. Might have seen a nice sorry everybody, phone keeps going off, gotta get rid of it. You might have seen a nice rainbow pattern when you see oil on water, and that is what we're going to talk about today. So let's do one of these questions. I'll show you how to do it. Whoops. Okay, so I'm traveling. It's in air, water, and let's say I have some glass down here. Okay, why? So when I go from air into water, some light will carry on, true, and some light will bounce back. Now this that bounces back, when I go from 1 to 1.33, it's going into something faster. Sorry, it's going into something slower. So when I go from fast to slow, the part that is bounced back will be out of phase by 1/2 lambda. Then light will come down here, and some will carry on into the glass, and some will bounce back. Now, yes, when I go from fast to slow here, some is going to go on unchanged, and some will bounce back. This part that bounced back, when I go from fast to slow, will also be off by 1/2 lambda. So currently both of these are out of phase from their other better halves by 1/2 lambda. And when I start getting this out of phaseness, I'm starting to get interference patterns possible, depending on how thick this is, how long it takes to go down and up. So let's try a question. So consider the following diagram. What is the thinnest film of soap that will produce bright light from the top of the soap film? I want bright. Yes, I'll write that right here. Bright. And hopefully you realize that bright is equivalent to constructive interference. So I got light coming in. It tells you its lambda is 411. Some will go in, some will bounce back. 1.35, fast, slow. The part that bounces back is off by 1/2 lambda. Some carried in, some carries into the glass, some bounces out of the glass. 1.35, 1.52, fast, slow. When I go from fast to slow, the part that bounces back is going to be off by 1/2 lambda. Now, I'm interested in lambda is changing. So I need to know what the new lambda is down here in the SOAP. So lambda in the SOAP is, or let's write lambda new, it was n old over n new times lambda old. Now the old n was 1, the new n is 1.35, and the old lambda is 411 nanometers. Now I'm not going to work that out. You can get out your calculator if you want, but it's fine for right now. So just need a bit more room here. If T was 0, if this thickness of the SOAP was 0, this one and this one, they would be back in phase again because they've both been shifted by a half lambda. I would be getting constructive interference if T was 0, but T is not 0. There is some thickness here. So this guy, this one right here, it's got this extra path to travel before it can start interfering with the light that's coming up from here. So I want constructive interference to occur. So currently, if T is 0, I would get constructive interference. They'd both be shifted by a half lambda, they'd be back in phase. These two things would be in phase with each other, but it's not. So how long does this light ray travel? It travels 2t. Yes? Down and up. To keep these guys in phase, I would need this plus this distance to be equal to lambda. And then crest would be meeting crest as they left here again. Again, this plus this, if it's equal to lambda, these two things stay in phase with each other. So 2t equals lambda, and therefore t is equal to lambda over 2, and therefore it's going to be equal to 411. I'm just taking this down here, over 2 times 1.35, and then I get an answer, and that's in nanometers, and I get an answer here. And you can use your calculator to do it. But this is how we do these questions, and we'll be trying. So you'll be trying some more soon enough. Some questions out of the textbook. One more question here I wrote. What about oil on water? Why is there a rainbow? Well, white light comes down. White light is all sorts of different colors. Got a pretty thin film here. Now if I'm standing over here, yes, watching, the path lengths that the different light rays will be taking in here and then reaching my eye will be slightly different. And so sometimes when I look down, maybe at this exact angle right here, I might be seeing red light, but if I change my eyes just a little bit and I look over here, it might be where constructive interference for orange light might be, and then yellow light. It's about so tiny variations, both in the thickness of this film of oil on top of water, but also in the angle that I'm looking at and the path length. When I look at different angles and how the sun is shining down, I'm going to get different path lengths in the thin film. So I'm going to get constructive interference happening at different places, at different angles, and that's why I would see a rainbow. All right, talk to you later. Bye.